All right, so Giancoli 5.6. Very similar to what we talked about in 5.5. So you'll like the math here. It'll be very similar. And we're talking about gravity near the Earth's surface. So we kind of went through this in class, but I'm going to make a video on it. So we can relate the gravitational constant G, knowing that the surface of the Earth. Okay, so this is mass of some item times G, which is the weight, force of gravity, is equal to our constant times the mass of some object times the mass of the Earth divided by the radius of the Earth squared. Why we use the radius of the Earth there? Because we're on the surface of the Earth. So the radius of the Earth is all there is. We cancel out our masses of the individual and we solve for G, and here's what we get. Okay, and this can be used to calculate the mass of the Earth. So let's say we want to find the mass of the Earth. We just solve it for ME, 9.8 times the radius squared divided by our constant gives us the radius of the Earth, which is what we've been using, 5.98 times 10 to the 24th kilograms. So it works out. This equation does make sense based on our number for mass of the Earth, okay? So that's what we go by. And this equation can be used to find the G for anywhere. Acceleration due to gravity will vary based on how far you are above sea level or at sea level. Like you're in New York City, it's a little bit higher, so you're a little closer to the sea than you are at San Francisco, or closer to the center of the Earth. And as you get farther away from the center of the Earth, the numbers will change, right? The equator, the Earth kind of bulges out, so you can see it's a 9.780, which is similar to being on Pikes Peak, 9.789. And so you can see that changing elevation slightly changes acceleration due to gravity, even though it's very unnoticeable. But mathematically, it does change. So here's an example. We're going to find G on top of Mount Everest, which is 8,950 meters above sea level. So that is, what is the acceleration due to gravity of objects allowed to fall freely at this altitude? We're ignoring the mass of the mountain itself, so we're just worrying about the Earth. Do it now. All right, so we've already done something similar to these problems, gravity on Everest. So instead of estimate, we're going to do it. We're going to find G on the top of Mount Everest, which is 8,850 meters above sea level. So what's the acceleration due to gravity of objects allowed to fall freely at this altitude? Again, the mass of the mountain is going to be ignored. So anytime we want to know G is going to be our constant times the mass of our planet, which is Earth, divided by the distance squared. Now the distance is going to be so let me show a picture. You got the planet itself, okay, and then you got the mountain, okay? So here's the top of the mountain. You got the distance from the center of the Earth, which is the Earth's radius, which is here. And then we also have the height of the mountain. So that's going to be our distance. We're going to have to add those two numbers together. So little g is our constant times the mass of the Earth, which is 5.98 times 10 to the 24th over our distance, which is 6,380, and then we add 8,850 to it. So we add 8,850 to it squared. And that should give us our acceleration due to gravity. Let's calculate that up. And I get slightly lower, right? Not much, but I get 9.77 meters per second squared. So a little farther away from the surface of the Earth, and our G goes down. And you can assume as we get farther away, G will also go down because that number will increase, which will make that number smaller. And that's essentially the types of problems you're going to see.